Okay, now we're going to look at the last section in Chapter 4, basically some applications of using exponential functions or log functions. The first is the growth and decay formula. Here, y equals y naught e to the kt. The y naught, the little zero naught, is the starting value, and k is the rate. If it's a positive number, then it's growth, and if it's a negative number, it is decay. Also, we have the formula for interest rate that we have seen before. P, the principal you put in, R, the rate, N, how many times it's compounded per year, and T, the number of years. However, if that interest rate is compounded continuously, then the formula changes to P times e to the RT, so we use the exponential function there, e to the RT. R still equals the rate, T the number of years, but the idea is it's been compounded not quarterly or monthly or daily, but continuously, like every second, basically. And so as an example, let's suppose that we have a deposit of 50,000 to produce a balance of 1 million. How long will that take? And so the 1 million goes on the other side because that's where we want to get to. The 50,000 is what we start with. The 0.12 is the interest rate per year. And so we're going to basically solve for finding t, how many years. So first we divide both sides by the 50,000. Million divided by the 50,000 gives us 20. So now we have e to the 0.12t. Remember that if we take ln of both sides, ln is the inverse of the exponential function. And so we end up with ln 20 equals 0.12t. Solving for t, we get just less than 25 years at 12%. And of course, if the interest rate is a lot lower than that, then it'll take a lot longer than that to get to that $1 million. Another example now is when we look at pH. pH is a log function. Basically, pH is the power of hydrogen. It literally looks at the exponent, 10 to the something, in the concentration, and then takes the log of it to turn it into a number that's in the single digits kind of area. So H plus is the concentration. Usually the concentration, well, values like 10 to the minus 7, 10 to the minus 5, 10 to the minus 9, those would be typical concentration values. The units are molarity, which is moles per liter for those of you who have taken chemistry. Now, we can go in the opposite direction as well. The concentration is 10 to the minus pH. So notice no base here, so that automatically means base 10, and the inverse for log base 10 is 10 to the exponent part. Finally, we have a third example in which we're looking at the way the volume of sound is measured in decibels. Here, log, again, base 10, and then this is I over 10 to the minus 12. The I is the intensity of the sound, which is basically power per square meter, and then the 10 to the minus 12 is a constant that we use to measure the quietest sound that people can hear. As in the case of pH, the intensity I can be found by making each side the formula power of 10. So first we divide it by the 10, and then we have 10 raised to the L over 10. Over here, 10 to the log. These, again, are inverses, and so we end up with 10 L over 10 equals I over 10 to the negative 12, and then we can solve for I. So over here, given the I, we can find what the volume is in decibels, and over here, given the decibels, we can find out what the intensity is of the sound. So again, this section is really just some applications of using exponential functions and log functions. So let us look at our examples here. First off, how long will it take an investment of 4,500 to grow to 9,000, basically to double, compounded continuously at 2%. 2% being maybe still on the high end of what you can get in a savings account or investment account these days. So let's start off with our equation. AT equals P e to the RT, again because we are compounding continuously. And now plug in our numbers. We want to get to the 9,000. We have started with the 4,500. Our rate is 0.02. Notice how the 2% becomes 0.02. And we're going to try to solve for the t. Okay, so if we divide both sides by the 4,500, that'll give us 2 equals e to the 0.02t. Now we take the ln of both sides, so ln2 equals ln e to the 0.02t, and then these are inverses, and so we'll now have ln2 equal 0.02t, or t equals ln of 2 over 0.02. ln2 on the calculator would be 0.693, and we would finally end up with our t equaling 34.7 years. There is, some of you may have heard, kind of a rule of 70. If you look at the interest rate and divide it by, into 70, you get approximately how long it would take to double. This is what we're looking at, going from 45 to 9,000. So approximately 35 times 2, that's our 70. So if our rate was up to, say, 5%, then we might be looking at more like 14 years instead of 34.7. If you get it up to 10%, then you're looking at 7 years. You know, and that's the power of compounding. But obviously, when the rate is very, very low, you know, I think today it's by the federal government, it's down less than 1%. It could take a very long time to double your money. All right, so now we're going to look at a decay type problem. Decay type problems, for instance, with half-life of radioactive material. And so here we have the half-life of bismuth, 210. The 210 refers to the mass of the element bismuth for this isotope. The half-life is 5 days, so that means every 5 days, half of this material will have decayed and will no longer be bismuth 210. So that means if we start with 10 grams, after 5 days, we would only have 5 grams. And after another 5 days, then we'd be down to 2.5 grams. So we cut it in half. That's why it's called the half-life. Well, we want to know, something not quite on the order of every 5 days. How much is left after 2 weeks, which would be 14 days. So not quite 3 times. And so we're going to look at our function here. So let's start off with 1/2 y naught equals y naught e to the 5k. Now, the reason that we're doing this is we have what the half-life is, but we don't actually have what k is at this point. Okay, we don't know the actual rate, and so we need to go through this process here to see based on 5 days, what will K be, so that we can figure out that particular rate. So, dividing both sides by the y naught. In other words, it doesn't really matter how much we start off with because we're cutting it in half. We now have 1/2 equals e to the 5k. And again, the 5 would be in the place of the t for 5 days. Now we're going to take our ln just as we did before. ln 1/2 equals ln e to the 5k. And of course, that gets us ln of 1/2 equals 5k. And therefore, k equals ln 1/2 over 5, which is equal to negative 0.1386. By the way, when you are doing ln, if you have fractions less than 1, you will get negative numbers for that. So now that we have what our k is, we can rewrite our formula to be 10. That's the amount we're going to start off with. E to the negative 0.1386t. So that's what our new equation would become. And now we can do it regardless, starting with 10 grams, for however many days we want. So 14 weeks, or 2 weeks, means 14 days. Since our original was in days, we have to do this in days. And so this will become 10e to the negative 0.1386 times 14. And that is 10e negative. When I go ahead and do the multiplication, I get 1.941, and that gives me 10 times, when I now go use my calculator, so I would be doing the e to the x, I would have to use the second key on this one, second, and then do that. So we would have e negative 1.941, and you can see how that comes out to the 0.1436. And so basically we would have 1.44 grams left after 2 weeks. So that's the idea behind decay problems. We started with 10, and after 2 weeks we had 1.44. Now after 15 days it would have been 1.25, half of 2.5. Note that you can't really, because this is an exponential function and not a linear function, you can't really just go, oh, it's like 14/5 of the way, or something like that. All right, problem 3. We have a concentration. Here's our concentration. Notice how concentration is usually done in times 10 to the minus something or other. In this case, -5. So this is going to be orange juice, slightly acidic. The units for molarity are moles per liter. We want to find out the pH. So basically the pH equals the negative log of the concentration. So negative log of the 6.31 times 10 to the negative 5. And that's a negative. The log part, because this is a negative 5 in the exponent, that will give me a negative in here. That's why we have an extra negative out in front of the log part to turn it positive, and so we end up with a pH of 4.2. And there's our pH. And then our last example here, the intensity of a sound generated by our alarm clock is 10 to the, this is actually an exponent, it should be 10 to the -4. So let's just go ahead and do that there. Watts per square meter. Find the volume of the sound, so we're going to find it in decibels. And then we're going to come back and say, all right, now the volume has been turned down to 50 decibels. What's its intensity? So first off, L equals 10 log. And we have I over 10 to the -12. And so now we're going to stick in our intensity, 10 log. 10 to the -4 over 10 to the -12. Remember from your exponent rules that when we divide, we subtract, so it's going to be -4 subtract a -12, and so that's going to end up being basically plus 12, -4 plus 12, and so now I have 10 to the 8, and so 10 times 8. Because again, since it's log base 10, I know the 10's not written, but log base 10, 10 and 10, that gives us the 8 there. And so we have, as our answer, L equals 80 decibels. Now, we take that sound and we turn it down to 50 decibels, so we want to see how that intensity would play out. We're basically going to go in the reverse direction. So 50 is going to equal 10 log I over 10 to the -12. So now what we're going to do is solve for the I. So dividing both sides by the 10, we have 5 equals log I over 10 to the -12. Now we take each side and make it the exponent. So 10 to the 5th will equal 10 to the log of I over 10 to the -12. Remember that for log base 10, the inverse is 10 to the x, and so these two will basically cancel out, leaving us with just I over 10 to the -12. And so I'm left with, I'll put it over here, 10 to the 5th times 10 to the -12 will equal I, or I will equal 10 to the -7 watts per meter squared. And so, a few examples of using logs or the e to the x function, exponential function.